Welcome to Chemistry with Dr. Z. In this video, we are going to talk about chirality in general and how to decide whether or not your molecule is chiral. So, what is chirality? Let's start with the general concept. So, everything has a mirror image, but mirror image may or may not be super impossible. Let's have some examples. So if you look at both your hands, the right and left hands, you can see that these two are mirror image to each other. However, they are not super impossible. If they are there, if a molecule or an object that is not superimposable on its mirror image is said to be chiral. So this is the general concept. Let's have another example, but this time for an object that has a mirror image which is superimposable. You can see that in a pair of socks. So two socks from a pair are mirror image to each other, but at the same time they are superimposable. So a sock and its mirror image are identical and they are not chiral. So any molecule that the mirror image of that molecule is superimposable on its mirror image is not chiral. And remember, any molecule has a mirror image. Any um, object has a mirror image, but the idea is whether this object or this molecule and its mirror image are superimposable or not. So let's apply this principle on actual molecule. So let's have a look at water. So water here, as we know, H2O consists of one oxygen atom connected with two hydrogens. There is a mirror image for water molecule. This is the mirror image for water molecule. But if you look at these two, they are superimposable on each other, which mean water molecule are not chiral. If we look at if we have a look at another molecule, which is bromochloromethane, this one. So this is the carbon atom connected to two hydrogens, and then we have a bromo or bromide, and then a chloride substituent. So these are the four substituent on the carbon atom. As you can see, this molecule here on the right hand side is the mirror image of the one on the left hand side. But again, if you rotate the bonds, then these two molecules will be superimposable on each other, which means that this molecule, bromochloromethane, is non-chiral, or we call it achiral, which is non-chiral. So how can we decide the chirality? Do we have every time to draw the molecule and its mirror image and decide, or to have a model and then play with that model to decide whether or not the molecule um, um, is chiral? Of course we don't. There is a very simple rule here. So let's have a look at the compound here. We have compound A on the left hand side. This compound here has a carbon atom and the carbon 2 in the molecule. This is 2-hydroxybutane or 2-butanol. This molecule, this carbon atom, carbon number 2, you can draw a mirror image for this molecule, compound number B. This is the mirror image for the molecule. But these two are not superimposable. So this molecule is chiral. How did we decide that? Can we decide that on paper? How can we look at a molecule and say, yes, this is a chiral molecule? If you have a carbon atom, a tetrahedral carbon atom, and tetrahedral carbon here means a carbon that has four substituents, that has four sigma bonds, not the carbon with a double or triple bond. If you have a carbon atom in your molecule and this carbon atom has four different substituents, as you can see here. So the substituents here are methyl, hydrogen, hydroxyl, and ethyl groups. Then this carbon is called a chiral center. So this is the chiral center. And this is carbon is stereogenic center, and these two molecules A and B, the molecule and its mirror image, are called stereoisomers, or we call them enantiomers. So what is an enantiomer? How we define enantiomer? So compounds which are superimposable, compounds which are non-superimposable mirror image to each other are called enantiomers. So basically, to find the enantiomer of a molecule, you just need to draw the mirror image of that molecule. Um, as long as this molecule has a chiral center. Again, the chiral center is the carbon, tetrahedral carbon, that has four different substituents. So this carbon atom as well, which is the chiral carbon, we also call it asymmetric carbon. Asymmetric carbon is the carbon atom that has the four different substituents like this one. So the four substituents, 1, 2, 3, 4, as you can see them labeled by different colors, are completely different. None of them is the same like the other one. And if you have this, then the mirror image for this molecule will be the enantiomer. So these two are enantiomers. These two compounds are different compounds because they are not super impossible in each other. They are completely different compounds. So there is an umbrella term for stereogenic centers called stereogenic or stereo centers. And this includes anything that will give you stereoisomers, because not only chiral compound are the stereo will give you stereo isomers, but also the double bond. So we know that if we have a double bond for alkene that have two different substituents on each carbon, then we can have the Z and E isomer. These are still stereoisomers. So we call this also a stereogenic center. And chiral center is one of the types of the stereogenic centers. In this video, we will use the term stereogenic center to refer to the chiral center. So if you hear me using the term stereogenic center in this video, then I am referring to the chiral center, but you need to also know that this is an umbrella term for any atom that will give you stereoisomers. So something like this tetrahedral carbon with the four different substituents is an asymmetric carbon, and it's a stereogenic center, and it's also a chiral center. This tetrahedral nitrogen with four different substituents is also a chiral center. Um, the stereogenic center here I'm referring to, as I said, I'm calling stereogenic center, I'm referring to the chiral center. So any carbon atom that is attached to four different groups. And here we're not talking about atoms, but two groups, so or substituents. So this is hydrogen here is a substituent. It's only one atom. Here, the second one, we will look at the whole group here that is attached to the carbon. This is a propyl group. I'm not going to look at the CH2 alone, but I'm going to look at the whole group. Again, on the left-hand side, you're going to have an ethyl group. So this is a different one. You cannot say this is a CH2 and this is a CH2, so they are identical. They are not, because we look at the whole group. And then the fourth one is the bromide. So this is a stereogenic center, this is a chiral center, and this is a chiral molecule. When you have a larger organic molecule, they could potentially have more than one chiral center. Sometimes even could have hundreds. Especially at the biological molecules. So biological molecules inside our bodies have so many different chiral centers. Some of the examples of these molecules are these structures here. So we have the uh, proproxyphene. So proproxyphene is an analgesic, and as you can see, it has two chiral centers. how did we decide that these two are chiral centers? Let's have a look. So we need to look at all the tetrahedral carbons. Ignore all the carbons that have double bonds. Ignore any other atoms. Just look at the carbon atoms um, which are tetrahedral, which have four different substituents, which are sp3 hybridized. So how many of these do we have? So we have this carbon, this second one, and the third one. We have a fourth one, five, and six. So we only have six carbons, sorry, and there is a seventh as well. So we have seven carbons here, which are all tetrahedral. So we need to look at them one by one to decide whether these carbons are chiral or not. This first one here, CH2, this is not chiral because it already has two hydrogen atoms which are identical, so it's not chiral. This carbon, the second one, this one has four different groups attached to it, so the one to the right hand side and the one here at the bottom, and then this is a benzyl group and this is a phenyl group. So you can see there are four different substituents, so this is a chiral center. The following carbon, this carbon as well, has four different substituents, so it's a chiral center as well. If you have a look at this one here, CH3, this is definitely not chiral. This is achiral because this carbon already has three hydrogens, so they are identical. So definitely it's not chiral. And carbon atom that has two hydrogens as well, CH2, is not chiral. So you can apply this to this CH2 and this CH3. Also these CH3. So all of these are achiral. So we only have two chiral centers. Of course, the carbon atoms within the phenyl groups here are not chiral at all because they are sp2 hybridized. There is a double bond. They are not tetrahedral. If we look at ephedrine is a bronchodilator and decongestant. There are also two chiral centers, these two carbon atoms. Each one of these have um, um, four different substituents. Um, the final molecule we're talking about here is the fructose. So fructose is a simple sugar and it has three chiral centers. This carbon is not chiral because it has to attach to two hydrogens, and this one is not chiral as well because it has two hydrogens, but the remaining three are all chiral. So how can we decide whether our molecule is chiral or not? We know that we can decide whether a certain carbon is chiral or not, but the whole molecule. Can a molecule have chiral center and not be chiral? Yes, it's a possibility. So how to design to consider to assign the molecule chirality? So we are not talking about atom chirality, we are talking about molecule chirality now. So if there is no stereogenic center, if there is no chiral center in your molecule at all, then your molecule is not chiral. But there are few exceptions, but I'm not going to talk about these here in this video. If you have only one stereogenic center or only one chiral center in your molecule, then your molecule as a whole is chiral. So we can talk about this molecule as a chiral molecule. If you have two or more stereogenic centers or chiral centers, your molecule may or may not be chiral. So it could be a chiral molecule as well. So if you have if there is a molecule that is achiral, um, then a molecule which is achiral, we can define this or we can decide whether or not a molecule is achiral if we can find a plane of symmetry in that particular molecule. So a molecule that has an internal plane of symmetry will be achiral, even though it could have one or more chiral no, it's not one. It could have two or more chiral centers. So what is the, so let's look at the internal plane of symmetry of molecule. If we align, so if we have a compound like this one, so the bromochloromethane, and we align the atoms in this, as we can see it here, and then we can have a plane of symmetry of the molecule. And the reason for that, because we have these two identical atoms, the hydrogen. The plane of symmetry will split the other two groups, which are the chloro and the bromo substituents. Um, you could, if you look at a molecule like that one, so if you have bromochlorofluoromethane. This carbon atom here has four different substituents. This one doesn't have any plane of symmetry. There are four different substituents and there is no plane of symmetry. You cannot have one half that is mirror image to the other half. So this is a chiral molecule. So some examples of molecule chirality. So the first one here is molecule A is methane. Methane, of course, is a carbon with four different hydrogen. It has so many different plane of symmetries, and definitely it's not chiral. So you can see the plane of symmetry here. If you have only one substituent, so like chloromethane, again, this is not chiral. There is a plane of symmetry as well, and the two halves will be mirror image on each other, so they're gonna be identical halves, so not chiral. If you have a molecule like dichloromethane, again, there will be two different plane of symmetry, as you can see here, molecule C. Molecule G is the one we talked about before, bromochloromethane. This is also have a plane of symmetry, one plane of symmetry, where one half of the molecule is identical or mirror image to the other one. But if you look at molecule E, which is the bromochlorofluoromethane with the four different substituents, there is no plane of symmetry. So, as we said, that if a molecule has two or more stereogenic centers, then this molecule may or may not be chiral. So, a molecule that has more than one stereogenic center will not be chiral if they have an internal plane of symmetry. So let's have a look at this molecule here. So this molecule, if we name it, it's 2,3-dichlorobutane. So 2,3-dichlorobutane. If you have a look at this molecule, so the carbon here, so let's give the carbon atoms numbers. So 1, 2, 3, 4 for the butane. Um, and carbon number 2 here is attached to four different substituents. So a methyl, hydrogen, chloride or chloro, and then this whole group. There are four different substituents. So this is a stereogenic center. This is a chiral center. And if you look at carbon number 3 as well, you're going to find that this atom here, carbon number 3, also have four different substituents. But actually, these two have an internal plane of symmetry. So if you draw the plane of symmetry here like this, you're going to see that these two halves are mirror image to each other. So this is an internal plane of symmetry. If you have a molecule that has an internal plane of symmetry, a plane of symmetry that will um, split it into two halves which are mirror image to each other, then this molecule is not chiral. It's achiral. And this type of molecule, we call it a meso compound. So these are called meso compounds and they will be super invisible on each other. So a molecule and its mirror image, so this is molecule 1 and this is molecule 2, and these two are mirror image to each other and they are also super invisible on each other. This is because they actually have a plane of symmetry. So if they have a plane of symmetry, internal plane of symmetry, they are not chiral.